Okay, this is exam 4 for physics 102. This is the WWP edition. Mirror produces an upright image. The object is 8 centimeters high, and to the left of the mirror, the image is 4 centimeters high. The center of curvature of the mirror is 16 centimeters. Where is the image located? All right, so a couple things we need to know here. First of all, I can tell you what the magnification is. I know, first of all, that the magnification is positive because it's upright. Next, I can also tell you what the magnification is just by the uh, the size. So the object is 8 centimeters high, the image is 4 centimeters high. So that gives me a magnification of plus 1/2. That means that this mirror, the only mirror that produces an image like this, is a convex mirror. So I also know then that the focal length, which is half the center of curvature, is 8 centimeters, is negative 8 centimeters because it's a convex mirror. And now I want to know, where is the image located? I want to know Q. All right, I know that M is equal to negative Q over P, and I know that 1 over F equals 1 over Q plus 1 over P. So what I want to do is I want to solve this. I have half is equal to negative Q over P. I want to know P, so I'm going to say, I want to know Q, so I'm going to say here that P is equal to negative 2Q. I'm going to take this and I'll plug it in here. And so I have 1 over negative 8 equals 1 over Q plus 1 over negative 2Q. Or rather, I'll just make this a positive and make this negative. All right, I can do a common denominator here, 2 over 2Q, so I get negative 1 over 8 equals 2 over 2Q minus 1 over 2Q, that's 1 over 2Q. And I get negative 2Q equals 8, cross multiply, Q is equal to negative 4. So Q is equal to negative 4. The object is 4 centimeters to the right of the mirror. It said that the object was to the left of the mirror, so the image is to the right of the mirror. So number 1 is D. That was a fairly difficult problem. The rest of them aren't that difficult. So a concave mirror has a focal length of 10 centimeters. An object is 10 centimeters from the mirror. Where is the image located? So I want to know Q. This is F. It's concave, so it is positive 10. The object, P, is equal to 10. Where is the image located? I just want to know Q. 1 over F minus 1 over P. That's 1 over 10 minus 1 over 10 to the inverse. That means that there is no image. Look, it's a concave mirror. Focal length is 10. The object is at 10. The object is at the focal point. No image produced by that mirror. So A is the right answer. Spheroid mirror has a focal length of 20 centimeters. If you stand 40 centimeters from the mirror, what is its magnification? So F equals 20, but this is a security mirror, so it's negative 20. That's a convex mirror. P is equal to 40. I want to know its magnification. First, I want to find Q. 1 over negative 20 minus 1 over P. Excuse me. 1 over, I'll go and write in P there. That should be 40. So the negative 1, that's 2 over 40 minus 1 over 40. That's negative 40 over 3 is my image distance. And now I want to know its magnification. The negative of negative 40 over 3 divided by P, which was 40. So those cancel. It should be negative 1/3. Let's see. Yeah, I just don't have the right answer here. It is negative 1/3. In fact, wow, I'll just change the options. But negative 1/3 is the right answer. So number 3 should be D. Or it should be negative 1/3. No, wait, that's not right. Hold on, give me a second. I will check this. I'm sorry, yeah, this is right. This should be positive 1/3. Okay, so number 3. Number 4, this shows an optical device and the image it creates. What kind of lens or mirror is this? Okay, well, first of all, I know that this has to be a lens because I have an inverted image. That means it's going to be a real image because M is negative q over p. If q is positive, that means m is negative, as it is here. So it's a real image, and the only thing that produces a real image like this is a concave mirror. Did I say lens? No, it has to be a mirror. It's the concave mirror. When the object is outside the focal point, it produces an image that looks like this. So the right answer for number 4 is D. Consider the rays drawn for this concave mirror. Which rays are drawn incorrectly? All right, so let's see here. Let's look at ray number 1 first. Ray number 1 goes parallel to the axis, and it should go through the focal point, but it doesn't. It goes through the center of curvature. So ray number 1 is not correct. All right, but let's look at number 2 and number 3 as well. Number 2, if it goes through the center of curvature, it should go back on itself. Okay, so ray number 2 is not correct either. Now let's look at ray number 3. Ray number 3 goes to the center and reflects. These two angles are the same. That one's okay. So D is the right answer. D is the right answer for number 5. What kind of mirror produces a virtual image that is smaller than the object? What kind of mirror? That's a convex mirror. That's like a security mirror where you're out here and you look really small. Which of these rays is or are drawn incorrectly? All right, well, this is a diverging lens, so these rays shouldn't be going towards the axis. They should be going away from the axis here as well as here. They should be going away from the axis. So so numbers 1 and 3 are incorrect. In fact, this ray right here, you don't draw it through this focal point. Remember, you draw it so that it goes through this focal point, and then it goes like that. All right, so 1 and 3 are incorrect, so D is the right answer. A concave lens, remember, looks like this. It only produces a virtual image. It is not a real image. It is not a magnified image, and it is an upright image. So C is the right answer for number 8. Convex lens has a focal length of 30. So a convex lens, oh goodness, what's that? Sorry. Convex lens looks like this. An object is 10 centimeters from the lens. P is equal to 10. Just a second. P equals 10. F equals, positive 30 for a convex lens. What is the magnification? So I first find Q. 1 over F minus 1 over P to the negative 1. That's 1 over 30 minus 1 over P. I'm going to say that's 3 over 30. That's negative 2 over 30, or negative 15 centimeters. So that's my Q. And now I want to find my magnification. That's negative Q over P, negative 15 over 10, which is positive 1.5. You could have looked at this. Well, no, never mind. Number 10, you have this double lens problem. What is the final magnification? All right, well, this is P1. So I have, first I want to find Q1. Q1 equals 1 over F1, that's 1 over 10, minus 1 over P1, that's 1 over 20, to the negative 1, that's 2 over 20 minus 1 over 20, so that's equal to 20 centimeters. All right, so and the magnification of that is negative Q1 over P1, which is 20 over 20, or negative 1. So my image is going to be 20 centimeters to the right here. It'll look like that. It's inverted and same size as the object. So if this distance is 20 centimeters, that means this distance is 30 centimeters, because they have to add up to equal 50. All right, so now I work the next problem. So Q2 is 1 over F2, that's 1 over 15, minus 1 over P2, that's 1 over 30, right here, to the -1. That's 2 over 30 minus 1 over 30 gives me 30 centimeters. And then M2 is negative Q2 over P2. P2 is also 30. That's equal to -1. So my magnification here oh, I'm sorry, no. Looks like it should be -1. Let me just a second, I'm going to double check this. Okay, yeah, it is supposed to be +1. The magnification total is M1, M2, which is equal to -1 here times -1 here, which is +1. On the test, I'll change this to be +1, so the answer for this would be number 12 will be D. All right. What causes mirage when you see while driving on a road? That's due to the refraction of light in the warm air. 13 then is A. Mirrors experience which of these aberrations? Mirrors do not experience these. They only experience spherical aberrations. So 14 is A. The human eye has a lens that can change its focal length. What is the focal length of the eye's lens the largest? That is going to be when an object is far away. So remember, the eye looks like this. When light rays are far away, the focal point is at the retina. When something is nearby, the focal length has to be shorter so that we can still form the image at the retina. And so in that case, our focal points are here and here, whereas here the focal point is back there. All right. When two waves are offset by 1/2 of a wavelength, they experience total destructive interference. That'll look like this. This distance is 1 wavelength. So being offset, that means the new wave would start here. So it'll look like that. That's destructive interference. These cancel out. These two waves are offset because they've traveled path lengths. By what amount are they out of phase? These are out of phase by 1/4 wavelength. Remember, this distance is 1 wavelength, so this distance is 1/4 wavelength. That is offset by a factor of 90 degrees. These two waves of wavelength 4 meters travel through space. The first wave travels 8 meters, second wave travels 4 meters. So the path length difference for these two waves is 12 minus 8, that's 4 meters. When they meet, what type of interference occurs? Well, this path length difference is equal to 1 wavelength, so they're going to experience constructive interference. In Young's double slit interference apparatus, by what factor does the distance between adjacent light and dark fringes change when the wavelength of the source is doubled? All right, so first we start with d sine theta equals m lambda. If I double this, I double my sine theta, I double my theta term. And then I say y is equal to L tan theta. If I double this, I double this. So if I double the wavelength, I double the distance between the fringes. So 19 is B. Here I have a double slit apparatus set up. I want to know what is the distance between alternating bright fringes on the screen. And actually, I think I'll change this on the test. And instead, it'll say what is the distance between the central and the first fringe. The same is true. It works the same, but I just thought that was a little more clear. But that distance is the same for any adjacent fringe. They'll be the same. All right. So see, I'll work it over here. I have, first I just want to find theta for the first order. So I say d sine theta equals m lambda, and I solve that for theta. M is going to be 1. Lambda is 630 nanometers divided by d, which is 0.04 millimeters, or 0.04 times 10 to the minus 3 meters. So then I can find my angle 2.9 degrees. And then I want to find the distance, this y, that's equal to L tan theta times L, which is 1.6 meters. I get 0.025. So B is the right answer for number 20. This figure shows a double slit diffraction pattern. What is the path length difference at this bright fringe? All right, this is the 0th, this is the 1st, this is the 2nd, so 2 wavelengths difference. Single slit is used to create an interference pattern. If you increase the wavelength, what happens to the width of the central bright fringe? A sine theta equals m lambda. If I increase this, I increase this, so it gets wider. Diffraction grading is this. What is its slit separation? 1 over 4,000. Is 0.00025 meters. And let's see, I want to convert, or that's not meters, that's centimeters, so I want to convert that 0.0000025 meters. That's 2.5 times 10 to the minus 6. What is the highest order maximum for wavelength that can be obtained with a grading with 600 lines per millimeter? Alright, so here I let theta equal 90, and this is a diffraction grading, 600 lines per millimeter. It's 0.0017. That's in millimeters, so I say times 10 to the minus 3 meters. That's my distance. Okay, sorry about that. So D is 0.0017 times 10 to the minus 3, and now I want to know what is M. So I know that D sine theta equals M lambda, so this is going to be D sine theta over lambda, but since theta is equal to 90, that just goes to 1, so it's 0.0017 times 10 to the minus 3 divided by the wavelength, which is 450 times 10 to the minus 9. That's 3.8. That means you have 3 orders present. If you don't have 4, you don't round up because you're looking for, it just goes up to 3 and then it stops. Okay, what angle? Second order maximum occur for wavelength 40 nanometers. Okay, first just want to find D, that's 1 over 10,000. Centimeters. Meters, move that decimal place over twice. And I'm looking for theta, so theta is inverse sine of m lambda over d. That's from d sine theta equals m lambda. And m is equal to 2, second order. Lambda is 400. And then this is 1 times 10 to the minus 6 meters. All right, yeah. And I'll do that. D is the right answer for 25. Here, this is caused by light incident on a circular object. And let's see, this is tough. I don't know. I guess A, maybe. All right, and that's the end.